bad. Microphone wasn't working. But it's fixed now. I don't know what happened. Okay. Yeah, recording will be not the best one. So next examples I want to give will need this kind of expected proposition. Something very similar to what we had for connected spaces. If you have a continuous function from x to y and x is compact, then the image f of x would be compact. So the proof will be essentially what we did for the connected case, but you need to like adapt the arguments, but essentially working the same. And as a consequence, any quotient of x, the one that we're assuming to be compact, is also going to be compact. And the proof for this will be homework also. And the idea is you can essentially assume f surjective. Don't really need in this case. And you can say, yeah, maybe let's not assume this. We don't need this. The idea why is this true is if f of x is inside the union of some ui's open in y, then pre-image x would be a subset, but actually equal to pre-images. And these guys are open in x. So this will become finite. Of course, this is not a proof. And then you just push things. Blah, blah, blah. And I'm probably only mentioning this because I want to include these examples, things that are quotients, s to the n, the sphere, S1 cross S1. We know that's a quotient. Remember, that's the torus. This guy is the quotient. You have like this square, and you're quotienting this with this and that with that. That's how you get S1 cross S1. What else do we have? RP2. So all these guys are compact because are quotients of compact things. Probably I'm still not sure why this guy is compact. But we'll discuss that at some point. Okay, so what's the elephant in these two whiteboards? We discussed compactness of pretty much any interval that you could have. Instead, those that are closed and bounded. So, fact for the future, any of these guys inside of the reals is compact. And that's the only interval that can be compact. And that's somehow the notion you should have in R or in Rn. Compact means closed and bounded. That should also be the case in any metric space. We don't have a theorem or anything, but that's kind of the meta idea you should have. Compact means closed and bounded. So we'll prove this at some point, so near future, either next time or Wednesday. But for example, this guy, which is just delete one point, is not compact. So what I'm trying to say is here we're inside of the reals, very nice space. You have a compact subset, subspace, but if you delete one point, then you're no longer compact. So the notion, the kind of question now is, when is a subspace of a compact space compact itself? And there is a very kind of easy criterion. I'm not sure if it's very useful, but in theory it is. Probably not in practice, but in theory it's very useful. So if X is compact and Y is a closed subspace, then Y will be compact. So let's prove this. How do we prove such thing? We need to take an open cover of Y. And instead of taking an open cover of Y, what I will do is I will use my lemma 1 that I probably just erased. Then let's see. That's going to be homework. Yeah, here we go. Instead of proving that X is compact, I can take opens in X, whose union contains Y. So I'm going to do this instead. Okay, so let U be a collection of opens in X. I'm doing this mostly because I want to show you how these things work. There's no very, well, there's kind of a clever idea, but not that clever. So let's take a collection of open sets in X that kind of cover U, Y, such that Y is inside the union of the U's. And what we like to do is we'd like to just find the finite subfamily of U that will still cover Y. Okay, if that's for Y, what do we know for X? What do we know for X? X. So we don't really know what we're missing by taking that union, because Y is a subset doesn't mean that's X, but X is Y union the complement. What's good about the complement? Maybe let's say what's good about Y. What's good about Y is we know we have this. That's for Y. But the complement of Y is open. So since Y is closed, X minus Y is open. And now we compute this. This means that if you append the complement of Y to this collection U, that's going to give you an open cover for X. Right? Everything here is open in X. If that's the case, you can stick with finitely many. So therefore, that being the case, we can just say, now I will need more space. If X is that union and X is compact, you can just stick with finitely many. And the thing about subcovers is once you have a subcover, if you add any other element in the cover, that will still be a subcover. And you will not lose finiteness if you just add one element. Yep. Absolutely, at least for finitely many. Absolutely. So I should say it should be clear for finitely many. Right. Because like if you cover the entire space, the entire product space with finite with an open cover, that means you should be covering each coordinate with a family, like project. But then that means each component can be covered with finitely many because each of those is compact. And then you can like pull back to the big space and you're done. If you have infinitely many factors, then you might be in trouble. Okay. Yeah, we'll prove that at some point. But what I was saying here is we have an open cover for X. Therefore, using that X is compact, we can just stick with finitely many. So there are some I1, blah, 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 IN. In lambda, there is no lambda here. There are U1, UN in U, such that. So in principle, I cannot say that X is just going to be the union of these guys, because I might or might not need X minus Y. But in the case, you can just stick it here. Either that was already true, namely you didn't need X minus Y, or it's not, and then you have it. Is that okay? So if there is a finite subcover, you can assume it contains one of your open sets. But if this is true, the only way for this to be true is for Y to be inside these guys. Right? Because elements in Y do not live here, but live in X, so need to live in the first union. So, and this is what we wanted. Exactly what we wanted. Okay, running low on time, but I still want to at least, yeah, I want to do this. I want to show you one idea, one clever idea for today. So proposition 4. The question now is, when is the converse of proposition 3 true? Is it true that if you have a compact subspace, that it needs to be closed? For example, that will be very good if you try to, for example, understand what are compact subspaces of the reals. So if you know something is compact, can you say something about it? And this is what we're going to do, but only assuming that X is Hausdorff. Remember, that means whenever you have two different points, there are open sets that distinguish them. So assume X is Hausdorff. If you have a compact subspace of X, then Y needs to be closed. Notice here, I don't need to assume X is compact. Of course, this assumption is needed. I won't say why today, but it's needed. So proof. Let's write at least some part of this proof. Because the idea, I really like the idea. So maybe let's start with saying, instead of proving that Y is closed, let us show that the complement is open. That's the definition of being closed. And this means something is open. Something is open if it's a neighborhood of all of its spots. X minus Y is a neighborhood of all of its elements. So we need to prove that. So let's take an arbitrary, let's call this X naught in X minus Y. And what we want an open, let's call it V in X, that contains X naught, and it's inside X minus Y. Okay, that's what we need to do. So the idea is how do we cook up this guy is something like, here's your X minus Y, the guy that we want to show is open. Here's your Y. These two guys do not intersect. Here's Y. And we want an open set with trivial intersection with Y. So the idea will be, for this X naught that we're fixing, we can take, for each point, arbitrary pointing Y, we can take two neighborhoods that will not intersect. So something like this, maybe. And then something like this. But no intersection between them. And the thing is, since this guy is compact, you will cover Y by taking all these neighborhoods, but you can stick with finitely many. That's not so important, but then you can take the finitely many guys that you have here, and that will not intersect Y. So that's the idea. Maybe I can write one for each Y in Y. We can take opens, X naught inside V naught, Y in, maybe let's call it Vy, Uy, and trivial intersection. That doesn't mean Vy is inside of X minus Y. Second part is Vy is the union of what I'm calling Uys. And this is just going to be finite because Y is compact. Maybe included. So this is just going to be finite. Y1, Yn. And then, since I have finitely many, I can take V naught to be the intersection of the corresponding V's. Vy1, And that will be open because I'm only intersecting finitely many. That's the important part. So yeah, we'll discuss this next time. It's a nice idea, but we don't have time to discuss it today.